Hello, we are BRACU Mongol-Tori from BRAC University, presenting our latest rover Polaris and our UAV Bumblebee for European Rover Challenge 2026. Representing thousands of hours of dedicated engineering, they are our most capable platforms yet, ready to tackle the absolute limits of planetary exploration.
BRACU Mongol-Tori is a multidisciplinary team of 67 students from diverse academic background. Our leadership core consists of a team lead, technical team lead, and team manager who together coordinate 8 specialized sub-team and their leads. Starting with hardware, the mechanical sub-team designs, develops, and fabricates the rover while also running stress tests to ensure structural reliability. Meanwhile, the electrical team handles PCB design, power management, wiring, and safety systems. To enable connectivity, the network sub-team develops the communication architecture using both commercial and in-house equipment. At the same time, the control sub-team builds the software stack and custom firmware for the rover's microcontroller.
On the higher level, the autonomous subsystem develops precision localization and navigation system for ERC tasks. Additionally, our science division is split into astrobiology and astromechanical units, covering both biological research and science hardware development. We also have a dedicated UAV department focused on the drone development, 3D mapping, and autonomous aerial navigation. Finally, supporting the entire team, the management, PR, and outreach sub-teams manage operations, sponsorships, and finances, while also organizing robotic workshops and seminars in schools and colleges.
Our pursuit of the European Rover Challenge is rooted in a simple belief: the greatest breakthroughs come from the toughest problems. Coming from the university that launched the country's first nano-satellite BRAC on Nisha, we carry forward a legacy of breaking new grounds. After 8 successful years in University Rover Challenge, we craved for an even greater one, the one that would test our entire engineering lifecycle. The European Rover Challenge demands absolute precision. The ERC's rigorous engineering, relentless autonomy, and documentation will be a proving ground for Polaris and Bumblebee.
Polaris is built on a 4-wheel rocker bogie suspension system, ensuring continuous ground contact and stability over rough terrain. Its chassis is constructed from stainless steel for durability and resistance to deformation. Our custom slotted wheels minimize debris buildup to improve drive efficiency. Internally, a ventilated aluminum box prevents overheating, while 3D printed enclosures isolate sensitive electronics from dust and debris.
The rover features a 7 degrees of freedom manipulator designed for precision and extended reach. A self-locking worm gear at the base provides a high torque and prevents backdragging for stable positioning. The arm operates on a horizontal linear rail for sub-millimeter accuracy driven by 3 base-mounted linear actuators to maintain a low center of gravity. At the end effector, a linear rail gripper and DC motor-driven wrist enables simultaneous controls. The entire module is interchangeable, allowing quick adaptation to different mission tasks.
At its core, Polaris is driven by a custom ESP32-based controller named Kachim that decodes Mabling commands over UART to execute more specific logic and calculate onboard inverse kinematics. The low-level architecture relies on a CAN-bus network to coordinate the robotic arms joint modules, which utilizes magnetic encoders for local PID control and telemetry feedback.
At the high level, a Python-driven ROS2 stack manages driver input, complex decision-making, and command generation. Maverick bridges this high-level logic with the low-level systems, while our ground station software enables real-life parameter updates. Ultimately, this seamless integration enables it to move forward, backward, right, left, and climb 40-degree slopes, safeguarded by an automated software kill switch that instantly halts the rover upon any communication failure.
In the event of any physical emergencies, Polaris also features an emergency stop switch that cuts off all power from the batteries to immediately cease all operations. The power system is designed for robustness and maintainability using redundant externally mounted hot swappable lithium-ion batteries with integrated battery management systems.
To ensure stability, the system is divided into 2 power rails. The first supports the high power needs of the rover's Cytron motor drivers responsible for operating the wheel and manipulator. The second rail powers a custom multi-channel power distribution backplane that monitors load across hot swappable eFuse DC-to-DC converter modules. A standardized system of vibration-resistant XT and locking JST connectors are used to pass all power and control logic, including Kachim's differential CAN bus, throughout the rover to maintain reliability during traversal. Key components including the science controller, Kachim, and encoder PCBs are developed in-house for rapid prototyping.
Polaris uses a layered localization and navigation pipeline that combines onboard sensing with real-time computation powered by the NVIDIA Jetson Orin Nano. It processes data from the Z2i stereo camera and the SVG Ellipse D GNSS. The system begins with global initialization using BRACU markers placed in a known 3D map. The Z camera detects these markers to estimate the rover's initial pose. If detection fails, the rover performs a rotational sweep to reacquire targets. As a fallback, the SBG Ellipse D provides RTK-corrected GNSS fused with IMU data, which is projected into a local UTM frame to initialize localization.
This estimate is then refined using normal distribution transform for point cloud alignment. For continuous tracking, stereo visual odometry is fused with IMU data through an extended Kalman filter. During navigation, NAV2 generates a global path, while a model predictive controller tracks it under motion and obstacle constraints. The Z camera derived point cloud continuously updates the cost map, enabling real-time obstacle avoidance and adaptive motion.
Polaris utilizes a frequency-diverse communication architecture for long-range, low-latency teleoperation. To ensure uninterrupted control, the system automatically makes transition between redundant layers. The primary video and control link operates over 5.8 GHz point-to-point connection backed by a high-gain 2.4 GHz network. In severely degraded RF environments, an industrial-grade 433 MHz telemetry link guarantees continuous and mission-critical command transmission. For situational awareness, our multi-stream vision system combines a 5.8 GHz digital FPV feed with multiple onboard IP cameras, allowing dynamic view switching. Operating on a 40 MHz channel width for optimal spectral efficiency, this tri-band architecture has been rigorously field-tested to ensure stable communication and seamless link recovery across extreme terrains.
For the droning subtask, we developed Bumblebee, a custom high-thrust quadcopter. At the core of its flight system is a Pixel 2.4.8 utilizing the extended Kalman filter for robust state estimation. To mitigate GNSS denial risk, the system employs an automated dual-source estimation topology. In the event of localized GPS instability or signal loss, the state estimator autonomously executes a failover to the optical flow sensor, ensuring precise hovering and velocity control. High-level mission logic is processed by an onboard Raspberry Pi 5 using an Intel RealSense depth camera. Our MATLAB algorithm performs HSB color thresholding and blob analysis to locate the scattered yellow-green probes. The mission sequence begins with a controlled takeoff, bringing Bumblebee to its operational altitude. Once in the air, Bumblebee demonstrates full control by flying smoothly along all three axes, front and back, left and right, and up and down. Following the flight maneuvers, we initiate the autonomous landing sequence. Throughout the entire operation, absolute safety is enforced by an 3D software geofence under any risky conditions. The pilot can immediately take manual control of the drone to safely navigate, backed by a deadman switch designed to instantly trigger an emergency autoland.
Leveraging its 7 degree of freedom manipulator, Polaris precisely operates lever and rotary switches, connects cables, and positions the electromagnet plate during maintenance tasks. Furthermore, our linear horizontal rail enables smooth lateral transitions between panels without needing to realign the rover chassis. To ensure operational precision, the end effector firmly grasps small objects, which is crucial for handling probes during probing tasks. Transitioning towards fully autonomous manipulation, our team is currently validating a next-generation BLDC actuated manipulator. This upgraded system will integrate harmonic drive to achieve near-zero backlash, drastically optimizing mechanical precision. Dual encoder architecture will ensure reliable positional feedback.
The science subsystem of Polaris execute mission and task on board, combining deep and surface sampling with environmental analysis. For deep sampling, an auger is deployed to extract targeted soil profile. The sample is deposited into a 3D printed container with an integrated load cell for precise onboard weighting. For surface sampling, the 7 degree of freedom manipulator swaps its gripper for a wide jaw cloth to collect regoliths and rocks. Each sample is stored in separated containers or is equipped with its own load cell for independent measurement.
In the astrobiology workflow, a liquid is extracted using a peristaltic pump into a sealed vial. The onboard sensor measures the pH of the liquid. The measured pH of the sample alongside geophysical and astrobiological data is used later to perform thin layer chromatography. Additionally, an atmospheric sensor continuously monitors ambient conditions, analyzing nitrogen, oxygen, light intensity, methane levels, atmospheric pressure, temperature, and humidity, which is displayed on the GUI in the base station. Additionally, orbital data from jammers is used to generate terrain maps, supporting mission planning and improving the scientific interpretation of collected samples.
Mongol-Tori's mission goes beyond just
just building rovers. We aim to build a supportive robotics community. Remembering our own early struggles, we are deeply committed to STEM education. Over the past year, we visited more than 20 schools and universities across Bangladesh to inspire the next generation. We also forged strong partnership with industry leaders.
As we wrap up, we wish the very best of luck to all the incredible teams participating this year. See you in BRACU!